Welcome back. If you're a lead design engineer, you already know that specifying materials is literally never just a simple multiple-choice question. Today, we're bringing you a brand new explainer focused entirely on advanced alumina ceramics. We aren't just going to sit here and read off standard spec sheets. Instead, we're taking a systems and dials approach to figure out exactly how you can select the perfect material for your absolute most demanding applications.
So, picture this scenario. You're holding two alumina components. They have the exact same dimensions, the exact same finish, and honestly, they look completely identical on the assembly line. But under stress, one of them survives for years, and the other shatters catastrophically in just a few hours. Why does that happen? Well, the secret is actually hidden in a microscopic world of grains, highly precise processing parameters, and trace impurities. To prevent those massive failures in your own designs, we've got to look beneath the surface.
Here's our quick roadmap for today's explainer. We'll be hitting 5 key areas: the purity microstructure link, impurity levers, electronic rolls, structural rolls, and finally, the trade-off matrix.
All right, Section 1. Let's dive right into the purity microstructure link and set up some foundational rules for bulk polycrystallinous alumina. Okay, every single material decision you make as an engineer basically relies on this one core concept: the processing-microstructure-properties triad. It's like a giant interconnected puzzle. It tells us that every manufacturing step you take, from the very first powder you select, right up to your final sintering temperature, dictates the internal architecture of the ceramic. And it's that internal architecture that directly governs the macroscopic properties you end up seeing on a spec sheet. You can't just pick a final property out of thin air. Instead, you have to tune specific processing dials to build the exact microstructure you need.
And you know, the very first dial you're going to turn is purity. On one hand, we've got technical-grade alumina, which sits at around 85 to 96% purity. Now, this grade is super cost-effective. It's a fantastic, versatile baseline for general industrial use. But if you're designing for truly demanding, high-performance environments, you absolutely have to pivot to high-purity grades. We're talking greater than 99.5% pure. Hitting that level of purity means extensive refining to pull out trace elements, which, yeah, definitely increases your costs, but as we'll see in a minute, it is absolutely crucial for unlocking superior electrical and structural performance.
Let's move on to Section 2, impurity levers. We're going to transition down to the microscopic battleground to see how adding impurities completely alters the ceramic system.
Now, this is where it gets really fascinating. Silica and magnesia basically act as completely opposing dials during the sintering process. You can use silica strategically to form a liquid phase that aggressively speeds up densification. It literally pulls the powder together into a solid block. But if you don't control it perfectly, it runs the risk of abnormal grain growth. You get these giant, weak grains that can easily start a fracture. On the flip side, we have magnesia. Magnesia acts like a strict bouncer. It segregates to the grain boundaries and locks them in place, inhibiting grain growth so the material reaches full density while keeping a really tight, fine-grained structure.
But hey, not all impurities are helpful dials you actually want to be turning. Take soda, for example, sodium oxide. Sure, it lowers the sintering temperature, but it strongly retards densification. It's a real problem, and it proves that your initial powder selection is absolutely critical. Because if your starting powder is contaminated with unwanted impurities like soda, your downstream processing and the final density of your component are going to suffer big time.
And this perfectly illustrates why we care so much about controlling grain growth with additives like magnesia. It all comes back to the Hall-Petch relationship. This principle tells us that a material's strength increases as the square root of the inverse of its average grain size. What does that actually mean for us? Simple. Finer grains directly correlate to a massive, totally predictable increase in your material's structural strength. To put that into perspective, by combining ultrafine grains with advanced techniques like spark plasma sintering, the flexural strength for alumina can hit a staggering 700 megapascals, just an incredibly strong material. That is the true power of microstructural engineering. Let's jump into Section 3, electronic rolls. We're moving from the micro reality to macro applications to see what alumina can really do in complex electronics. If you are the one specifying materials for things like hybrid microcircuits, insulating packages, or high-voltage vacuum feed-throughs, well, these are your non-negotiable dials. You've got to start with that high-purity alumina,
greater than 99.5%. You need an internal structure that is completely free of any conducting secondary phases to keep that dielectric loss super low. Plus, from a pure design standpoint, you have to carefully manage the CTE, the coefficient of thermal expansion. If you don't manage that mismatch, your ceramic is going to crack the second it's bonded to semiconductor metals that expand at different rates.
But the payoff for hitting those strict requirements is huge. The extreme volume resistivity of high-purity alumina exceeds 10 to the 14th ohm meters. That effectively stops leakage currents dead in their tracks, making alumina just a phenomenal, highly reliable insulator for high-temperature and high-frequency electronic gear.
Moving right along to Section 4, structural roles. Let's shift gears to mechanical applications where the environment is harsh, it's corrosive, and it demands extreme durability.
When you're designing mechanical parts, think pump seals, valve bodies, or cutting tools. Your whole priority list shifts. Here, your ability to precisely control that grain size is literally the difference between a part surviving for years or shattering the moment it takes a load. You're shooting for a really high Vickers hardness, usually right around 14 to 24 gigapascals, along with killer wear resistance. But definitely pay attention to those last 2 points. Alumina is brittle. Your design absolutely must keep the component primarily in compression, minimizing any tensile stresses to avoid a brittle fracture.
Just to really hammer home that design constraint, look at how alumina handles pressure. It is an absolute tank under compression, easily exceeding 3,000 megapascals. And that is exactly why your mechanical designs have to avoid sharp tensile stress concentrators. If you can keep the forces compressive, high-purity alumina is going to act as an indestructible workhorse for you, even in highly abrasive environments.
All right, final section. Section 5, the trade-off matrix. We know no material is perfect for literally everything. So let's see how alumina stacks up against competing structural ceramics.
When we line these materials up side by side, alumina's Achilles heel instantly jumps out: fracture toughness. Alumina sits pretty low at roughly 3.0 megapascals root meters. Silicon carbide is only a tiny bit better. But look at zirconia all the way up at 12. If you were designing for an environment with cyclical stress or heavy, high-impact hits, zirconia is your clear, unequivocal choice to stop cracks from spreading.
The way zirconia achieves this massive toughness is actually mind-blowing. It uses an advanced transformation mechanism. Basically, when a crack tries to form, the crystal structure at the tip of the crack physically transforms and expands, literally squeezing the crack shut. You do sacrifice a little bit of overall hardness compared to alumina, but the advantage you gain against brittle failure is completely game-changing. But hey, the entire story flips if we start talking about thermal conductivity. Say you're designing heat spreaders for high-power electronics. Zirconia is basically a thermal insulator sitting at a 3. Alumina is okay, hanging out in the middle at 32. But silicon carbide is just in a league of its own, hitting 120 watts per meter Kelvin. It completely dominates high-temperature thermal management.
So the engineering trade-off we have to make becomes crystal clear, right? You want to leverage alumina as your versatile, cost-effective baseline. It gives you this incredible balance of hardness, electrical insulation, and chemical stability. But the second your design faces extreme impact demands, you've got to pivot to zirconia. And if you run into intense thermal loads or high-temperature wear, you pivot to silicon carbide.
To wrap up today's explainer, I want you to walk away with this simple 3-step framework. You can use this to systematically match the microscopic reality of the ceramic to the macroscopic needs of your application. First, define the primary failure mode you're worried about. Is it wear? Is it heat? Or is it an electrical breakdown? Second, pick the optimal baseline purity grade to handle that specific environment. And third, work closely with your manufacturing partners to actively engineer the microstructure, using the precise impurity dials and processing routes we just broke down. So I'll leave you with this thought. How are you going to apply the processing-microstructure-properties triad to optimize your very next high-stakes component design? Please don't just default to whatever's on a standard spec sheet. Get in there, take control of the dials, and engineer it from the grains up. Thanks for hanging out with me for this explainer, and keep engineering with purpose.